Welcome and thank you so much for joining us for this Tech Talk with Schlumberger and Equinor. Today's discussion will be about intelligent wireline formation testing. I am your host for this broadcast, Jason Notoris. Audience, this is all about your engagement as well. We really want to hear from you, so make sure that you comment. We also have polls that you can participate in for this Tech Talk. You're going to have an opportunity also to ask questions in a live Q&A as part of this broadcast. So we're excited to hear what you have to say, what your feedback is, and the questions that you have for today's guests. So for today's Tech Talk, we also do have those two poll questions that I was talking about. They can be found in the LinkedIn event. All you have to do is scroll down to the bottom of the event page. Question 1 is, deep transient testing on wireline adequate to evaluate minimum hydrocarbon in place? Love to hear your feedback on that. Also, question 2 in the polls, does the industry have the right level of solutions co-development between operators and service companies? If you have additional commentary, just click the comments button and let us know what you think. Those questions, again, are on the bottom of the LinkedIn event page. You may need to scroll to the bottom in order to vote. So let's get to it. Joining me for this Tech Talk are Kåre Otto Erikson. Kåre works for Equinor as a senior specialist in exploration. And about 15 years ago, he embarked on a journey with Schlumberger. The goal was to produce deep transient testing solution on wireline. Also on today's SPE Tech Talk is Partouche, a wireline formation testing product champion for Schlumberger. Ashers has been working for more than a decade to bring the solution to life. And today, we're lucky because both of us are going to join us to talk about the collaboration between these two companies that made deep transient testing on wireline a reality. Welcome to the SPE Tech Talk. Thanks for joining us.
Good morning, Jason, and good morning, everybody.
Morning.
All right, I'm going to let this first one be a toss-up, so either one of you can take it. I think it'll be really important just to set the stage. If you could provide a quick introduction to just what deep transient testing wireline is.
Sure. If you want, Kåre, I would take that one. So deep transient testing is a new solution that we developed that would allow us to bridge a gap between the information that we have on that we can achieve with wireline formation testing and dual stem testing. I believe there is an animation that can be shown in parallel to that, right? So, and so this is really what we are, we have developed over the years, leveraging the Aura platform. Through the development that we've done with Equinor early on, we developed that solution that allows us to be able to see deeper in the formation using wireline technology. And what does that bring in terms of advantage is that it allows us to get this type of information that you would get with dual stem testing in terms of reduced intensification, hydrocarbon in place, possibly even deliverability and reserve booking without the need of flaring at surface. So this can be done without this type of flaring emissions, as well as because we are still fundamentally deploying it on the wireline type of technology, it's a much faster and lighter footprint to develop. So at the same time, we're able to reduce the time it takes and the energy consumption that results. And of course, as we leverage the Aura platform, we have a digitally enabled platform that allows us to have live planning and live execution, digital execution of the service.
Thanks for providing that. It's some good insights to get us started. Hopefully that gets some of the audience's brains, just ticking a little bit here in the morning for anyone who's just getting into the first cup of coffee. So as far as your relationship, am I to understand that when all of this discussion first started happening, you two didn't really know each other, right?
Yes.
Right. Correct.
So at what stage in the project did you first meet and know that the partnership would be something that would be successful?
Are you asking me or is?
Yeah. Well, yeah. Kåre, go ahead and take that one.
Right. When you're muted, Kåre.
No, you can start, Archie, and I can take it.
Okay, all right. So I think no, indeed, we didn't know each other when all of these projects started about 15 years ago. But Kåre Otto is a well-known expert in information testing, and he reached out. The Equinor reached out to Schlumberger and to develop a solution that allows them to have this type of deep transient testing result. Especially because of some environmental challenge that there is in the North Sea, where there is a restriction in the ability to flare. So there was no really solution, and the goal was presented to us to go from the wireline formation testing capabilities that we had, and stretch that to be able to get to this information that was at the time only available with deep transient testing, and that's when this collaboration started, and there was this co-development to develop first, a solution, find out what the problem was, develop that solution, validate it, and eventually it migrated to when I joined on the project to develop the integration into the Aura platform, which is our newest intelligent wireline information testing platform.
You hear about that a lot, where teams are almost doubling work, whether or not they're within the same company or across different companies. But I mean, look at what can be accomplished. You two are testament to that. When we do meet, we communicate and we share ideas. So Kåre, I'm interested to hear your take on this then. How did the concept of deep transient testing on wireline originally get developed, where this teamwork started to kick into gear?
Yeah, okay. Yeah, now I've been working for quite some time, and when Schlumberger introduced MDT back in the 90s, we saw a huge step up there in improvements, and of course that was into how to do pre-testing and fluid sampling, etc. in the beginning there. And it then took out a lot of the incentive for doing DST testing, which was one of the main objectives back then. To get the fluids, because the RFT type technologies didn't give us the sufficient quality. So that was a big step up with the MDT coming in. And then we started to see there was a lot more benefits in this, we called it mini DSTs. A lot of people asked, why do we call it DST? It's not a DST, but that was to acquire this dynamic data to explore more. And then when we started to see that with development with dual packers, vertical interference testing, we developed new software to interpret the multiple sets of data with integrating both the observation data and the actually coming from the packers, the probes. And we saw that, wow, here is a big potential. And then in the early 2000s, we had a lot of issues with, first in the Arctic, we were not allowed to do DST testing. We needed to get other alternatives. So my project back then was to go into 3 different ways, either to do more smart testing, get more zones out of DSTs, get that more efficient, or we developed or start developing this extended closed chamber testing with this big tubing and a pig that is you move up the well to have a large volume closed chamber with downhole sampling and pressure gauges. And then alternatively, what can we do with the wireline formation testers like the MDT mini DST? And then we did a lot of mini DST testing, and we started to realize more and more that there is some issues here. We do have problems with the gauge resolutions. We have well noise. We see quality issues in some of these cases. What can we do about that? And then we started to investigate. Okay, what is creating these artifacts and this well noise and all these things? Should we do something with the gauges to improve the resolution? Maybe that was not a good idea because there was so much other noise, well-related things that is overgoing the gauges itself. So let's see what we can do about that. And that was the start, talking with Schlumberger and see can we do improvements here, because we think there is potential. And then we systematically started to map out what is the problem, what can we do. And we knew that we need to create bigger pressure pulse into the reservoir to allow the gauges to pick up this signal out there far further away from the reservoir. Then we need a bigger pressure pulse. How do we do that? We need to have higher flow rate. We need to even improve the quality. Also, we need to have a bigger volume takeout to get the better, receive better the effects of the reservoirs out there. We need to get rid of the tool noise or the well-related noise, and then we see that we have plugging inlet on the quartz gauge. We only have a strain gauge. That is maybe not good. We have to look into that on the dual packers. We need to see what happens if you change the pressures in the packers for the intervals that you're reading the reservoirs. Is there an interference there? How these are connected? Can we do something about that? And then we also realized that with running gauges below the packers, above the packers, we saw that the pressure was not equalizing on the packers. That introduced a big down force on the tool that is slightly moving the tool, creating noise. All these things was kind of systematically looked into, and that was the start of and to be able to have a higher rate, we need to get rid of the oil or the gas because of well control. So how can we get rid of that? We then started to investigate with our mud engineers everything. Can we pump more into the mud and circulate out without this coming into a situation where well control or anything destroying the mud? And was very surprised that there is a lot we can do to pump more into the well and circulate continuously while we're pumping. So that was the start there, and we got all the disciplines, Schlumberger and Wireline and information testing, and of course the dream in the beginning was to develop a solution on pipe. So that was the beginning of this project, and of course the way we set it up to try to come to the solutions was extremely well set up by this collaboration and Schlumberger. We started that back in 2005. Took a long time to develop, improve what I saw was the limitations with the MDT technology as it was. We built that into what we called FTVT, which had higher rate. Pumps had the possibility to pump at much higher, larger volumes. We used those pumps back into the MDT to have a larger flow rate, but over limited volumes, and we saw that working, and that is the way it developed. And as I see it personally, is that all these good things that was made into an FTVT prototypes, which was built back then, those improvements has been later integrated into the Ora platform, both the Wireline tool and now the Ora Deep Transient Tester. And the nice thing is that when you have this ruggedized power package that can provide power to pump at high rate, we have built pumps that can give higher rates. In the Ora, we have now included the gauges upgrades and these bypasses and everything that was introducing these problems in the past, which less chance of plugging, that you start to get movements on the pack. All these upgrades that was done is very nice, and when you do the Deep Transient Tester, which is the topic here, we also take the benefit of all these upgrades on the Wireline tool, all these modules, that the scanner, fluid scanners, a lot of the other modules, even the pumps that's in there can go into the Deep Transient Tester, and that makes things more efficient than the availability. We only need to have this ruggedized TLC system for high power cables, the circulating subs, and some of the other components that make this possible as a deep transient tester. That's the good thing about this.
Thanks. Thanks, Kåre. I mean, this is very.
You're muted.
Yeah, Jason, you're muted.
Sorry about that. So yeah, I mean, I can just tell your passion for this because I can see Oshers, you had that big smile on your face the entire time. I guess maybe part of it could have been because I was on mute there for a second. But
no.
For the discussion, I know the audience is really enjoying it as well. It's a nice opportunity to really sink our teeth into this. Do want to thank the audience for responding to the poll. So if we just take a quick moment to look at how those results are going. I'm interested to hear, gentlemen, both of your perspectives on what the results have been. And thank you for everyone watching. I see, from Houston, Mexico, Turkey, the Woodlands, India. Thank you, everyone, for watching around the globe. The first poll question results have come in so far. Let's look at this. Let me refresh the page just to make sure we have the most up-to-date answers. Does the industry have the right level of solutions co-development between operators and service companies? And we got about 60% saying yes right now. I'm wondering if a lot of that is established connections that people are relying on versus new connections. But where I want to really get your feedback is the votes that have come in so far for, is deep transient testing on wireline adequate to evaluate minimum hydrocarbon in place? And it looks like 2 out of 3 people are saying yes. What's your reaction to that?
I think what we have shown, and I would like Kåre comment as well, but what we have shown in our field testing of ORAD deep transient testing is that operators are trusting ORAD deep transient testing to be able to give them the information they need to estimate the reserve. Of course, it's dependent on the formation response as well, but we've seen that with the ability that we have with the ORAD deep transient testing, the ORAD platform itself to flow extensively up to 108 barrels per day. And with our recirculation, active recirculation that Kåre Otto mentioned, so that we can circulate those hydrocarbons to surface continuously, we are able to flow for much longer. And with the improvement in the pressure gauge, we are now be able to see with a better resolution much farther in the formation, up to 600 meters in depth of investigation. So with all that together, yes, we believe as well that ORAD DTT is adequate to measure, to make reserve estimations, and I'm glad that our audience is also agreeing on that.
Yeah, maybe with this tool, you might need to do several station testing to understand how the things varies there, how the vertical connection is, and any tight barriers there, are they laterally or not? Now so we maybe have to do multiple zone testing to get it, and we can get everything from some few hundred meters, maybe up to 1,000-meter investigation. You should be able to at least see if there is more segmentations or heterogeneities in that area, and if you see those, then you could have an issue. But to have the full STOIP in a larger structure of even a DST is very often not possible to come up with something else than maybe a minimum volume like that or more. So of course, if you are, the main objective is to get a STOIP, then an extended well test maybe be the solution for that particular case. But you do get a lot of information about the complexity of the reservoir by doing it this way, as I see it.
And briefly, could you add to that then? Because I know we've touched on how this technology is environmentally friendly, just what that means specifically.
Yeah, because now that was one of the drivers for starting to develop for example, for me, the FDVT, which is now integrated all in ORA, is that we could not do DST testing in the Gulf of Mexico where we are operating. We could not do DST testing in the Northern Arctic Barents Sea where we operate there. So that was a problem. And now, of course, this new climate crisis that comes in, and we are promoting the company to try to have minimized the CO2 print in the industry, how we are operating and trying to reduce as much as possible. We are not flaring during production. We try to cut down on emissions in many all possible ways. So to not burn 10,000-15,000 barrels on a DST, it doesn't look nice out there. So this would be good in that sense also to have some alternatives to get the dynamic data we need.
No, I mean, I agree. I think what we've seen is that, one, because we're able to perform this measurement without the need of flaring, we are cutting significantly down on the amount of emissions. We've estimated that, in general, when we compare to a deep water operation, the DST, to a deep transient testing, we can cut up to 96% of the carbon emissions resulting for the operations, right? And that is mostly because of the reduction in flaring, but also because we are cutting down on the time it takes to do the operation.
Yeah, exactly. And for example, if we did a couple of these jobs in the offshore Newfoundland in very harsh climate, weather and things, and of course with these deep water rigs, DP operated, which is using a lot of fuel on sitting on the location. So if we can reduce the number of days on the well, it's really also saving not only the flare off, reduce the flaring on testing, but also to cut down on the time we are on the wells is also important. And also, for example, a couple of the wells we had down in Brazil, ultra deep water and things, when you do DST testing, you have issues with 1,000, 2,000, 3,000 meter risers full of oil. If something happens on disconnect and things, there is issues there on the HSE environment that it is a risk, even if we have ways to come around, but you have an exposure to do full DST testing on ultra deep water. We did one gas test in very, very deep water. There is also issues with the safety on doing, because of the hydrates and the pressure down at the sea bottom on doing gas testing on the DST with full production to surface. So if you can use this technology to take out some of that, it's also very important, I think.
Thank you both so much. I'll move to some of the audience questions because some really good questions are coming in from the audience. Let's start with this one. So for some of the radius of the investigation, by how much is the pump out volume reduced compared to conventional DST?
Yeah, we, typically we can down to less than 100 cubes of oil is pumped into the system, because if you have the max, I guess you can do, if you have say a 200 cubic meter active mud system, you cannot take in more than 50 cubes, 50,000 liter into the system if you are operating like that. There is a limit on the amount, but we probably take out less, maybe 20 cubes or something in total production, 20,000 liters. Could be 170, but that's a lot better than only 500 liters that you did with a conventional MDT mini DST before you had issues with wipeout drips and get rid of the hydrocarbons in the well. We are maybe can up to 1,000 liters. So now we are talking about a lot higher volumes takeout and higher rates than what we have done in the past.
And we've had a couple of questions come in about TLC, start at the top. So can this be run in just wireline, or do you need a TLC for the technology?
So maybe we can move to the slide 2. I think it's a nice illustration of how it works. So we have to have the wireline cable is always present to operate the tool, but because we want to recirculate, I don't know if the animation can play. I think on slide 2 the animation doesn't look like it's playing, but basically because we are trying to recirculate, we need to have a way to convey the mud circulation down and mix with the formation fluid, right? And that, you can see it from the animation, is achieved through the pump. As we pump the fluid from the formation and we expel it out, we can recirculate at the circulation sub, and that's through the drill pipe. So to answer your information, we are always connected with the wireline, but we have to convey with pipe to be able to bring the fluid and recirculate. Now, there is the ability, if in some condition where the volume pump is not as much of a constraint, that we could have a very large, use our large flow rate pump just on one line without the recirculation, but that's going to depend on the specific application that you're looking at and your specific condition in terms of how much hydrocarbon you allow in the wellbore.
Yeah, but just a comment, I have to be honest to say that when the Wireline tool came around, which had the high pump rate capability and improved gauges, etc., of course, then it takes a chunk of the commercial FTVT that we built, before, because the FTVT had a high pump rate compared to the MDT. Now the Wireline tool have the capability of high rate as well. So then you can argue, why bother doing this on the I call it the FTVT version of the ORA, which is the Transient. Why bother doing that? Because you are running in on pipe when you can do a lot on Wireline. But yes, some of that will be taken care of by the new upgraded platform ORA. So yes, to test higher mobility reservoirs because of the higher pump rates. But again, if we take very small volumes at high rate, then you introduce a pressure pulse in there. Maybe you can see further in, but you know, if you have a very low volume takeout, you may not see what you want to see out there, and you get better data set to look at, and quality of this transient data, they are better when you are increasing the volumes.
Yeah, a follow-up to that then from Kåre is, you know, I guess they're asking, you know, you've been doing with dual packers, just confirming that. But what about the spacing?
Oh,
yeah, that's a good question. Maybe I address that to Schlumberger, because, you know, that worried me, because when we developed FTVT, we developed the quad packer, which is a 4-packer setting that is not possible or recommended run on wireline because of the sticking risk and the weight and everything and the friction to pull those packers. So they were only run on the FTVT in those days. And that was for many reasons, to take out a little bit of these differential pressures that was limited on the old MDT with less differential pressure than the new Ora has upgrades there, but also to take out some of the well noise and get the cleaner data set, and we have less flexing around with those packers that is sitting on the test interval itself. Yeah. But you know what we found out then, to get a much better vertical interference, which is extremely important, that you have both these data sets when you're downscaling the testing like we do here now, to get a more unique data set for the models, that you reduce a lot of options for interpretation when you are having 2 sets of data like we now have. So we were sleeving off one of those 4 packers that it's not inflated, so we increased the test interval, and we had a very short distance to the interference, the vertical interference, which in many of the reservoirs, whereas, you know, we shouldn't have a tool that you have to look for a reservoir that fits the tool. We need to have a tool that fits the reservoirs.
Yeah.
So then we realized to have that vertical observation on just 1 meter above on that. Then we had 3 packers set, gave a very, very good data set for us. In addition to, you could have a normal VRT probe above there or below there to get even better data to investigate if you have some. So this how we use it now is it's great, you know, that you have that kind of data to work with.
So I mean, Kåre, you'll be happy to hear, right, that Aurora Deep Transient Testing platform, on Aurora platform, we have integrated the ability to increase the spacing up to 15 meters, right? So depending, as you said, right, we should not have a formation that fits the tool, but the tool should be able to be flexible enough to address your formation needs, and that's what we built in the Aurora platform. So we have the ability to put the standard spacing, add spacing as you want incrementally, all the way to 15 meters to capture the type of zone that is of interest.
And that's the good thing here, as I see it also, is that if you want to test very low permeability, and you need kind of a pack with whatever meters of spacing, then to because is this mobile water, is this mobile oil, we don't know, and the pumping, and you have a very low rate because of the low mobility, and you have segregation, and it takes 1 day to even fill up the spacer packer interval to get some fluid into the flow line, into the fluid scanner. You know, it takes 18 hours, 20 hours to now you can switch around. That was also a dream we had on the improvement on the MDT when we built the activity, to have multiple inlets, or you can switch between the inlets, high, low, whatever, if you are looking for mobile water here or is mobile hydrocarbons. So you can, and in addition to that, you can also get the fluid that you want to get into the samples in a much quicker way. Okay, you can clean up with high rate faster, yes, but you can also speed up the clean out just to have these multiple inlets, saving rig time. So just that small detail is extremely a big improvement, as I see it, to the wireline technology in general on this. So yeah.
And I think that Brad Beach has summed this up pretty much for all of us, in the fact that he said that this is collaboration showing a great way to describe this journey, and it's great to see developments continue. Cheers from Indiana. Brad, I don't know if you're a Hoosier, Boilermaker, Sycamore, Fighting Irish, something else, but thank you for your comment. Completely agree with that. And thank you so much audience for all of your participation in this. Kåre, Ashers, appreciate you taking time to educate me and the audience on this. It's really been just a tremendous discussion all around. And then thank you also to Schlumberger and Equinor for sparing both of you and your time to be able to share this information. Really, really do appreciate speaking with you today.
It was a pleasure, Jason. Thank you, Kåre, Otto. Very nice to talk to you again.
Yeah, same.
Thanks, everyone. We'll see you on the next SPE Tech Talk.